Okay, so 7 asks this thing, Q versus R less Q. Okay? So, precisely, the quotients, right, the rational numbers are what? What was your characterization for a rational number?
Can be counted.
R divided by Q, or
Yeah, it's
some number divided by another number divided by
some number divided by another number. But why isn't pi in Q then? Because pi is pi over 1, right?
That's an irrational number divided by plus b.
So it should be a
An integer divided by
an
another
integer divided by a.
integer.
You don't want to divide by 0 though, right?
Is the real zero a whole number?
So I think you can get away with this, right? You can get away with the idea that the top should be an integer and the bottom should be a counting number.
What are those symbols you're using?
Oh, you guys don't know these ones?
I don't know that one.
That's a
Well, actually, no,
Oh.
I don't know the other one.
Okay, so this is good to know.
natural number.
This is real, right?
Yeah.
Let's see, what else do I have? I have Q's. Q's are that. Q's are the fractions, or the rationals. Z is the integers. N is the natural numbers, right? The counting numbers, the numbers that label herds of sheep.
That doesn't include 0, right?
Yeah, the natural numbers don't include 0. If you want to include 0, you want this one that's in between here, which is this one. W standing for whole. So the whole numbers contain 0, the natural numbers don't. I do not care at all if you know this one.
Don't the natural numbers only contain positive counting?
Yeah, the natural numbers are the numbers of sheep that you can have in a herd. Right? Possible sheep herds. And that's it.
As long as it's a herd. Once there's 0, it's no longer a herd.
Yeah, once there's 0 sheep, it's not a herd of sheep.
You can't have negative sheep.
And so you can't have that in there. And
Anti-matter
you can't have anti-sheep. Anti-sheep come up in the integers. Okay, so anyway, these are the things. There's one more. What's the other one I'm missing up here?
The
Irrationals.
Well,
The complex numbers?
imaginary numbers.
What about the irrational?
Yeah, so the irrationals are the ones that are in the reals but not in Q.
Oh.
Hence the R less Q, or R take away Q. You could write that this way. Some books do this thing. Look at that. Like literally grade school takeaways.
Little e's that contains all.
Okay, so here's an argument for these things are smaller than those things. First things first, I need to demonstrate to you that these things are countable. In other words, these things have the same number of things. You guys cool with this? Okay, so I made this little crosshatch, and I'm going to do this with it. I'm going to put 0 over 1 there. And then here I'm going to put 1 over 1. And then I'm going to put 0 over 2. I'm going to put 1 over 2. And then I'm going to put 0 over 3. And I'm going to put 1 over 3.
Oh, and you continue this off.
Right, so I'm going like that. And then, so what's this one?
2 over 1.
That should be 2 over 1 and 2 over 2
2 over
And-
3.
2 over 3 and so forth and so on and so on and so on. And then down here I'm going to put negative 0 over 1. Oh, what the hell? I'll skip the negative 0 row. So I'll put negative 1 over 1
Negative 1 over 2.
and then there should be negative 1 over 2 and so on and so on and so on. Yeah, this is kind of a little funky slope field. This is just, so this is not a graph, right? This is just me throwing numbers into a box. And I should note that there are kind of rows and columns. Did I get all these things in there? Like, where's negative 37 over 3 going to be in that picture?
Where's way?
Just down to the
Way
right.
down.
Way down a bit to the right.
See, so I need to go down to the negative 37 row, right? And then across to the 3 column. You guys all see that? Have I missed any numbers doing this?
Oh, I see.
I don't
It's
think
the
so.
irrationals.
Yeah, so there's no irrationals in here. This is all just the fractions, right? But have I missed any of the fractions? Have I got a couple twice?
Yes.
Yeah.
More than twice.
Yeah, I have a whole row, right? That's just the number 0 written lots of times. Okay, but this is at least as many as the fractions, right?
Correct.
You guys see that? Like Q sits in here. And so now I'm going to label these with natural numbers. So I'm going to go like this. I'm going to say, this is the first one. This is the second one. This is the third one. This is the fourth one. This is the fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20th, and kind of so on, right?
There's theoretically a countable number.
You guys see that? So what I'm arriving at is this infinity and this infinity are the same kind of infinity. Yeah, so that's a countable infinity. So they're the same number of things, and we're going to call that number of things countable number of things. Or maybe countable
You have to
infinity
count
of
in
things.
different directions, because if you want to count up, you're counting. But now, if you want to count closer to 0, you're still counting. Like there's no start. How do you determine the starting point? Is your
I
starting
did determine a starting point, right?
point was
I
0?
determined that I started with 0, and then the next one is also 0, and then the...
Yeah, but like, where's like 1 over a million? Like that's not met. It's somewhere in there.
Yeah, and I could figure out where, right?
Second row.
You guys see that? Like,
As long as there's
I'd have to go into the second row and down that way, and then I'd have to fold this thing out until I find out what number I assigned it. You guys notice my pattern wasn't quite consistent at the beginning?
Yeah.
That bothered the heck out of you?
Yeah.
But it doesn't matter because it's still countable.
Yeah, so usually you just fold that around somehow, right? It doesn't actually matter how you do that folding, as long as it's consistent.
You would be able to count it if you had an infinite amount of time and resources.
But
Right.
that's the whole
It's the idea that you can count to the number if it existed, but it's not. It's infinite.
So the other kind of infinity is this.
The arrangement of.
Yeah, so let me just do this. So I'm going to look at the closed interval from 0 to 1. Guys cool with this?
Okay.
And I'm going to think about this as decimal expansions in binary. You guys all believe that numbers have decimal expansions in binary?
Okay.
Yes.
Do you all believe that all the numbers between 0 and 1 have decimal expansions in binary?
What does the in binary?
What does that mean? It just means that all I'm going to use is zeros and ones because I don't want to use... Oh, what the hell.
Just decimal.
There, how about that? Do you believe they have decimal expansions?
Yes. I just.
Okay, so the 0, 1 is 0.000, right? And so on. And the one for 1 is 1.00 and so on. Yes? Okay. Assume that there was some listing, right? Assume that someone had supplied you with this 1, 2 thing. So that's the first number, that's the second one. The third one is, I don't freaking know. The fourth one is whatever it is. The fifth one, the sixth one, and so on, right? So you have to assume that someone gave you this. Then what I'm going to show is that they're wrong. You guys see that? So what I'm going to do is I'm going to make a new number that I'm going to call Steve. Okay? And my number Steve is going to be different than all the numbers in the list, which means that whoever claimed they made this blue list didn't do it right. Because they missed this one. You guys see that?
Okay.
And then they might try to argue with me. They would say, well, just throw Steve in the list in the first spot and scoot everything down one, right? But then I would say, well, hell, I can make a number Steve plus 1 that you also missed in the exact same way. And yeah, you can throw that one in, but then the number Steve plus 2 that you make in the exact same way also won't be in there, and you clearly haven't done this right. You guys all see that? Okay, so the way we're going to make our new number is we're going to look at our decimal, and we're going to do not 0 here. Pick any number. I do not give any crap what it is.
7.
Okay, so you're going to put 7 there because it's not 0, which means that Steve is not the first number in the list. Oh,
That doesn't.
I screwed up.
0.7.
You guys see this?
Yeah.
I wanted to make this open. Let me just say that there's some number here. I'm going to start Steve with a 0 so it's actually in the interval I
So
was
it's
talking about.
0.7 now.
Yeah. So then I'm going to make this not 0 because that's this first one. And then I'm going to make
Yeah, I see it too.
this one not 0 too.
3.
Yeah, whatever. And then I'm going to say this one was 0.2334, whatever. What's the next digit?
8.
Yeah, exactly.
Theta.
So not 3, right? So it can be 8. That makes it different than this one. You guys see that?
Yep.
So Steve is definitely not in that list. So they made that list wrong, right? Which means that any list that was made this way can't be right. You guys all see that?
So it's not countable.
So this has a not countable number of things. Okay, and then we were actually trying to get at R less Q, right? So R, right, is made of things like this, right, intervals. So I had a not countable number of things, and I took out a countable number of things. So how many things are left?
I didn't count it.
Still not.
It better be not countable, right? Because otherwise you could fit the list for the result and the list for the things you took out together like this. Right? You take the list for the things you still had, and the list for the things you took out, and nest them together and get a countable number of things.
So is it kind of an idea of like nested infinities sort of? Or?
Yeah, exactly. So what we know is that the number 1 is less than the number 2, and so on. And then there's this concept of infinitely many things, right? And this might be the countable kind.
I just want to cover that.
And I know that that's smaller than this kind, which is the uncountable kind.
There's an uncountable and uncountable infinities.
Okay, and then if you're smart, you'll ask the next question, which is what?
Is there an
How many ways
uncountable?
can you arrange that countable and uncountable infinity for each thing?
Yeah, so is there a next one is a good question. And is there one in here is a good question. Right, like this is, I have a number, call it 3, and another number, call it 7. Is there 5? That's actually an open question. So the open question precisely phrased is the continuum hypothesis, which is to say that is the next kind of infinity after countable the same as the number of real numbers? We don't know. We don't know.
What do you mean the same cardinality as real?
Yeah. So is the next infinity after countable the same as the number of real numbers, Or is there an intermediate thing between, I know it wouldn't be countable, right? So it's definitely uncountable. But really I'm wondering about this equal sign under here for the number of real numbers, right? You guys see that? I don't know if there's one of these or if all of these are that size or bigger. You guys see that? It's super cool, it's still open. The only thing we know about it right now is that you can't prove it using the usual axioms of set theory. Meaning that all of the tools that you guys have played with in math are not going to answer this question. You have to go to a different place to start. Cool?
You have to be a next dimension.